In this lecture, we're going to do some applications of theory of elasticity to the wave equation, talking about stress waves and solids. And in this particular lecture, we're going to focus on writing the equilibrium equations in terms of displacements. We'll see why we want to do this when we get to the wave equation in a little bit. But first, just let's start off reviewing what our equations of motion are for a continuous body. So if we have a continuous body and we have conservation of angular momentum, we can write our equations of motion equations as sigma ij comma j plus bi is equal to rho ai, where sigma ij are components of the stress tensor. The comma denotes partial differentiation with respect to x sub j, where there's an implied summation. We have the body forces per volume, bi, and it's equal to rho, the mass density, times ai, the acceleration components. If we want to specialize this to equilibrium conditions, then our rho ai term will go away, and we'll just have sigma ij comma j plus bi. Just as a reminder, the repeated subscript j means that we have an implied summation from 1 to 3. I is a free index in this equation. Let's go ahead and write down our equilibrium equations just to kind of review them. We have three of them: the partial derivative of sigma 1,1 or sigma x with respect to x, plus the partial of the shearing stress tau xy, or we can call it sigma 1,2 with respect to y, plus tau xz with respect to z, plus a body force term. If we're writing it out in terms of coordinate directions, we can call that capital X instead of B1 equal to 0. And I'm going to write down the next two. And there we have our three equilibrium equations. Now, since we are taking a class in elasticity for this discussion, we want to restrict ourselves to isotropic materials, and we're going to look at linear elastic isotropic materials. In general, you don't have to have isotropic materials. You can be anisotropic, but we're going to kind of keep things as simple as we can for now. Okay, so our Lemay coefficient form of Hooke's law is sigma ij is equal to lambda e Kronecker delta ij plus 2g epsilon ij, where e is the trace of the strain tensor. We call that epsilon kk. Let's just put a little squiggle underneath that to represent that, to avoid any confusion later on. So little e is a trace of the strain tensor. Kronecker delta ij is 1 when I and j are the same, 0 when they are different. And lambda and g are Lemay coefficients. If we want, we can write out our stresses. Let's go ahead and do that. So sigma x would be lambda e plus 2g epsilon x in terms of our coordinate directions. In a similar form for the other two normal stresses. And for our shearing stresses, of course, when we have x and y, that's like sigma 1,2, Kronecker delta 1,2 is 0, so the first term disappears, and we're left with 2g times epsilon xy. And these strains, these shearing strains that I have here, epsilon xy and so forth, those are tensorial shearing strains. Those are half of the engineering shearing strains that we would ordinarily think of. So we have these three shearing stresses now in terms of these shearing strains. The other thing that we'll need are strain displacement relations. We'll go ahead and write those down as well. We will be looking at small displacements. We'll have the small displacement assumption. Which is suitable for this discussion. So we have 1/2 the partial of ui with respect to xj plus the partial of uj with respect to xi. In terms of our coordinate strains, we can write down 3 normal strains. Of course, we have terms like the normal strain epsilon x is equal to partial of u with respect to x. Epsilon y is the partial of v with respect to y. Epsilon z is a partial of w with respect to z, where u, v, and w are the 3 displacement components in the x, y, and z directions. And then we have our shearing strain terms that look like this. For the tensorial shearing strains, we have 1/2 partial of u with respect to y plus the partial of v with respect to x, and so forth. And I'll write these next 2 down. All right. So let's take a look at our first equilibrium equation. And that's this one right here. We have the partial derivative of sigma x with respect to x. So we have an equation for sigma x right here. We're going to take a partial derivative of that with respect to x. So we have the partial derivative, and now lambda is a constant. So we have lambda, the partial derivative of the trace, little e with respect to x, plus the material constant 2g. And then we have the partial derivative of epsilon x with respect to x, but epsilon x is the partial derivative of u with respect to x. So now I can just write this as the second partial derivative of u with respect to x twice. The second term in our equilibrium equation is the partial of tau xy with respect to y. Now tau xy is this equation right here. And we want to take the partial derivative of it with respect to y. Alright, so we have 2g, we have epsilon xy. Epsilon xy is this term right here. Now the 2 and the 1/2 cancel out. So we have g and then we have the second partial of u with respect to y plus the second partial of v with respect to x and y. Okay. And then in our third term, the partial derivative of tau xz with respect to z. Here we have the equation for tau xz. That's 2g epsilon xz. Epsilon xz has 1/2 partial of u with respect to z plus partial of w with respect to x. The 2 and the 1/2 cancel out. So we just have plus g. And now we have the second partial of u with respect to z twice plus second partial of w with respect to x and z. And then we can put in our body force term if we want, and then equal to 0 for equilibrium. Now if we look at these terms carefully, here we have the partial of little e with respect to x. And remember we said little e, let's write it down here somewhere. Oh, here it is. Little e is the trace of the strain tensor. So we can say little e is epsilon x plus epsilon y plus epsilon z. Or it's the partial of u with respect to x plus the partial of v with respect to y plus the partial of w with respect to z. So the partial derivative of that with respect to x, let me move my toolbar. It's going to be a second partial of u with respect to x plus a second partial of v with respect to x and y plus the second partial of w with respect to x and z. I know that's kind of tiny in there. My apologies. Let me clear this up just a little bit. And if we look at these terms, we have here the second partial of v with respect to x and y. That's the second term right here. We have in here a second partial of w with respect to x and z. That's this term right here. And we have two second partials of u with respect to x twice. That's this term right here. That's part of it. So what I can do, we have a g that's common to each of those terms. So I'm going to rewrite this just a little bit differently. I'm going to write this as lambda plus g, and this is the partial derivative of the trace with respect to x. And then we're going to have plus g times, we have partial of u with respect to x twice, partial of u with respect to y twice, partial of u with respect to z twice. Let's go ahead and write all those down. And if we remember what our gradient is, that second term is del squared, the displacement component. Well, hang on. I made a little mistake here. These should all be u's. So this is that was the first term in each of these equations. So these are u, and this is u. Okay. So this term right here is del squared u. All right, let me clean up a little bit of room here, and let's talk about this again just a little bit. All right, just to say this again, here we have lambda times the partial derivative of the trace of the strain tensor with respect to x, and then we have 2g, second partial of u with respect to x, we have this mixed partial of v with respect to x and y, mixed partial of w with respect to x and z. One of these plus this term and this term is equal to the partial of the trace with respect to x, and that has a common factor of g. So I pulled that out in front, collected the terms, so I have lambda plus g, partial of the trace of the strain tensor with respect to x, plus g times the leftover terms. I have one of these that are left, second partial of u with respect to x twice. I have this term, second partial of u with respect to y twice, and this term, second partial of u with respect to z twice. Now, you may recall what our gradient operator is. Let's go ahead and talk about that. In 3 dimensions, our gradient operator is partial with respect to xi plus partial with respect to yj plus the partial with respect to zk. It's like a vector. When we do del dot del, that is what we're going to represent as del squared. And of course, when we do del dot del, we're multiplying the common terms. We have the partial with respect to x twice. We have the partial with respect to y twice. We have the partial with respect to z twice, sitting here waiting to operate on something. All these things added together. And it's, in this case, waiting to operate on the u displacement. So all of these together represent del squared u. Now, if we want, we can do this for the other equilibrium equations as well. We do them one at a time and then combine them. What I'm going to show you next, however, is a little bit of a shortcut. We're going to use our index notation to help us come up with our equations. Let me start off with a fresh page. Alright, so at this point I'm assuming that you're pretty familiar with our index notation. So let's use Hooke's law and write our equilibrium equations in this index form in terms of Hooke's law. So here we have sigma ij comma j plus bi is equal to 0, and sigma ij is equal to lambda e Kronecker delta ij plus 2g epsilon ij, where little e is a trace of the strain tensor, which we can write in terms of displacement as partial of uk with respect to xk. We also need our small strain definition. Epsilon ij is equal to 1/2 partial ui with respect to xj plus uj with respect to xi. Alright, so let's put this into our equilibrium equations. We want to take the partial derivative of sigma ij with respect to xj. So if sigma ij is equal to this, let's do that. Lambda, now e, lambda is a constant, so we don't have to worry about its partial derivative. We're going to have the partial derivative of little e with respect to xj. Help me keep an eye on my subscripts. And then we're going to have Kronecker delta ij. And then we're going to have plus taking a partial derivative, we have the partial derivative the first times the second, and then we're going to have the first times the derivative of the second. So it's a partial derivative of Kronecker delta ij with respect to xj. And then we're going to have 2g partial derivative of epsilon ij with respect to xj. And then plus bi is equal to 0. Now this Kronecker delta ij is a constant type term, so it'll go away. Just wanted to kind of show that in there for completeness. So we have lambda partial derivative of e with respect to x j plus 2g partial with respect to xj of the quantity one-half partial of ui with respect to xj plus the partial of uj with respect to xi, plus our body force term bi is equal to 0. And before I forget, I need to make sure I have my Kronecker delta ij in there. Now the Kronecker delta ij acts as a replacement operator on indices, so I can actually rewrite this first term as lambda partial of little e with respect to xi. Now the 1/2 and the 2 in the second term will cancel each other out. So let's rewrite this again one more time. Where I distribute this partial derivative through, I have g times the partial derivative of this term, ui with respect to xj, with respect to xj, and then the g and the partial derivative with respect to xj of the next term, partial of uj with respect to xi, and then the body force term tags along equals 0. Let's go ahead and take a look at these terms one more time. We have lambda partial of e with respect to xi plus g. We have the second partial derivative of ui with respect to xj and xj. There is an implied summation there. And then we have this last term, g, and we have the partial derivative with respect to xj. And that second term, partial of uj with respect to xi. Well, let's see. Let's write it this way. The order of differentiation isn't important. So I am going to take this I and move it over here. And the second term will be the partial derivative of uj with respect to xj. Now there is an implied summation in that term as well. Let me write it up here. I have lambda partial of e with respect to xi plus g, second partial of ui with respect to xj and xj, an implied summation. And then on this term I have g, and you see we have the partial of uj with respect to xj. Those are 3 terms. That is the trace of the strain tensor. You can go back and look at some of the previous slides, but you can see that that's a trace of the strain tensor. So what I have is the partial derivative of the trace of the strain tensor with respect to xi. It's the same as the first term, plus bi equals 0. So if I want, I can collect some of these terms. I can write it this way. Lambda plus g, the partial derivative of the trace of the strain tensor with respect to xi, plus g, second partial of ui with respect to xj and xj, and the body force term. And if we think about it, we can see that the second term is nothing more than del squared ui, where ui are the displacement components in the 1, 2, and 3 directions, where I is the free index. Move this over here. Now, if we want, we can take another derivative with respect to xi, lambda plus g, the second partial of the trace with respect to xi and xi, plus g times the third partial derivative of ui with respect to xj, and xi, plus a partial derivative of the body force term with respect to xi. Now we do have some repeated indices, we do have some summations. Now, if the body force terms are constant, then we could do, we can have this term equal to 0. And what we have then is lambda plus g, second partial of the trace with respect to xi and xi, plus g. Now we have the third partial of ui with respect to xj and xi. If we want, we can change this just a little bit and write this in terms of the trace of the strain tensor. We can have that written as the second partial of the trace in terms of x j and xj. And let me think if this 2 needs to be in there or not. That 2 will not be in there. Okay. And we can work with this a little bit more. We can write this as lambda plus 2g del squared, the trace of the strain tensor, is equal to 0. And we can do a little bit more work with this. We have lambda plus 2g here. Since that's equal to 0, if we have constant body forces, then we can say that we have del squared E is equal to 0. Or second partial of the trace with respect to x twice, plus the second partial of the trace with respect to y twice, plus the second partial of the trace with respect to z twice is equal to 0. Now, let's remember what the trace of the strain tensor is. Little e is epsilon x plus epsilon y plus epsilon z. It's a measure of the dilatancy of the material, or the measure of the volume change of the material. Now, we could have just as easily started off with non-equilibrium conditions with our differential equations of motion. In which case we'd have sigma ij comma j. If we neglect body forces, let's do that, is equal to rho ai. And a is acceleration, so that's the partial derivative, the second partial derivative of displacement with respect to time. I need to put here neglect body forces. And so we can write this as sigma ij comma j minus rho second partial of the displacement ui with respect to time is equal to 0. And we go through and we can do all that algebra again. And we could get lambda plus g partial derivative of the trace with respect to xi plus g del squared ui minus rho second partial of ui with respect to time equal to 0. Now I is a free index. That's actually 3 equations. Now suppose we have no volume change in the material. Then its partial derivative with respect to any one of those spatial coordinates would be 0. So that first term would go away. When the first term goes away, we have g del squared ui is equal to rho second of ui with respect to time. And we get our first of our wave equations. All right, we'll talk a little bit more about this in just a little bit. So I'm going to pause here. We're going to take a break on this video, and we'll pick this discussion up again with the next video.